UN, pues obviamente nuestra universidad, y en este caso 70 por los 70 años. De modo que no digo más, yo creo que lo que hay que hacer es pues disfrutar mucho, porque va a haber mucha matemática esta semana. Como les decía, hay teoría de modelos, geometría aritmética, geometría algebraica, algo de análisis, algo de probabilidad, ciencia de datos, y obviamente no quisiera cubrir todo, pero yo creo que es bastante lo que se va a cubrir en estos 4 días. Informaciones prácticas, de pronto iremos un poco más adelante. Recuerden que hay una pausa café por la mañana y una por la tarde, y un bloque de 2 horas de almuerzo, cada cual quien quiera. Y adicionalmente, quería mencionar, ya para cerrar, al nuevo equipo organizador, que básicamente, como les decía, extendió lo que venía siendo hecho desde antes por Reinaldo. En este caso, el profesor Alexander Cruz fue esencial, sobre todo en la etapa inicial, en varias etapas, en la etapa inicial de concepción de lo que queremos en este buen encuentro, y también en muchas etapas de organización. El estudiante de doctorado, José Nicolás Naja, que está ahí verde, pendiente de muchas cosas como ven, también ha sido esencial. De la facultad, pues, y todo el equipo, digamos, de medios, Tania Arias en particular y mucha otra gente. Hay todo un equipo detrás de esto, y es lo que hace esto posible. No digo más, arrancamos entonces con las primeras charlas de la mañana. So, welcome.
Porque no, todavía no están listos.
Una vez que lo pongas en el
pero apagado.
pon el primer slide.
Eso no se puede hacer. Eso es perfecto. Y el micrófono un poquito.
Entonces, bienvenidos todos. Welcome everybody. Esta es la primera sesión del Buen Encuentro. Es realmente un placer para mí presentar a Xenia de la Osa de la Universidad de Oxford. Xenia es reconocida por su trabajo en física matemática principalmente. De hecho, debería mencionar que este año se cumplen 35 años del artículo de Xenia Philippe Green and Parks, que es como para la gente que trabaja en Mirror Symmetry, es el punto inicial del estudio matemático de Mirror Symmetry. Entonces, en realidad es un placer tenerlos aquí también para celebrar su artículo. So, if I can, now I say in English, so welcome, my pleasure to introduce Xenia de la Osa from University of Oxford. So Xenia is best known for her work in mathematical physics. And this year is the 35th anniversary of his paper with Philip and another, which is actually the starting point of mirror symmetry. So Xenia will talk about black holes and the arithmetic of family of Calabi-Yau varieties, connection between number theory and physics. So please, Xenia.
Thank you, Alex, for the introduction. Thank you very much. It's a great pleasure for me to be here, an honor actually, to be here celebrating 70 years of the mathematics department. I mean, this thing to be celebrated like this. I think so good for you. So I can only repeat that I'm very happy to be presenting here. So this is the first part. So these are two consecutive talks. The second will be 3 minutes. And it will be about connections. The main takeaway is that I want to illustrate connections between mathematics and physics. Right? I will talk mainly about the connection between geometry and arithmetic of certain families of algebraic varieties that are called Calabi-Yau manifolds. There is a deep connection between the geometry of these spaces and the arithmetic of these families. The common theme will be of mathematical objects called periods, which I will define. And Philip then will talk about the connection between this and physics, right? In particular, the connection with black hole solutions in string theory. So these are my collaborators across the years in these connections between mathematics and physics. Those in yellow are my early career researcher collaborators, the graduate students at the time, and our graduate student at the moment. Okay. Fine. Okay, so this is a table of contents. What do we do with that?
We have to wait probably 16 seconds. Let's say.
So okay, so this is the table of contents, roughly speaking, of what I will say. I'll start with the arithmetic of the right varieties. I mean, there is an object called the zeta function associated to these varieties over finite fields. Then I'll go into the geometry and discuss what are these objects, these Calabi-Yau manifolds, and the geometry and the periods. And then I'm going to go back to the arithmetics and discuss the Calabi-Yau manifolds over finite fields. And see how, in this story, one ends up counting points for finite fields. And then there is a very important number in Q, which is discounting precisely. And we will see how that can be written in terms of periods. So there is this is the connection between the arithmetic and the geometry, and periods are determine also the physics of this black hole solution. So this is a triangle there. That is extremely interesting. So Philip will talk later about the arithmetic of what's called attractor varieties. And this is also a story about how mathematical concept called the Hodge structure changes. And I'll discuss at least intuitively what these things are. So let's start with zeta functions, right? So see, in algebraic geometry, one is interested in the geometry of varieties defined by polynomial equations, right? For example, we have y squared plus x squared plus equals, sorry, x cubed plus ax plus b, where a and b are complex numbers, and the x and y take values over the complex numbers. And this has this polynomial, and this has a very nice geometry. This is an elliptic curve. Right? If you think intuitively the surface of a torus. This is a very important object in algebraic geometry and number theory, and is in fact the simplest Calabi-Yau manifold. I'll define that later. So the mathematical objects of interest today will be algebraic varieties, That means sets of solutions of polynomial equations in some ambient space. So this X bar means a point in the ambient space. It can have n dimensions. So X bar means X1, X2, X3, Xn. And so these will be, at this moment, they are polynomials with complex coefficients. And this will give you some geometry, right? So this is a caricature of what's happening for an ambient space, and you have the zeros of the locus of the polynomial. Notice the yellow number here, right? So these are parameters that in this context are the coefficients of the monomials of the polynomials. Now, Cavaglia manifolds that the ones we will discuss are algebraic varieties that have special properties, and I'll discuss that. I'll discuss what special properties are later. For the moment, let's just talk about algebraic varieties in general. So let's suppose that we have a family of algebraic varieties, parameterized by the number 5, defined by a polynomial, like the one we had before in an ambient space. Now let's suppose that instead of 5 being a complex number, let's suppose it's a rational number. So now we ask, so this is a very natural question for number theory, right? How many solutions of the polynomial are there over Q, right? That's one question. The second is, if you can find this number of solutions, how does that vary as you vary this by parameter 5? So as it turns out that even for this elliptic curve, this is an extremely difficult question. Right? Is for elliptic curves, for example, this leads to, for example, a Millennium price problem, right? In particular, the Verge and Swinnerton-Dyer conjecture that is related to estimates of discountings for elliptic curves. So it's very difficult, right? So, but however, what the number theory does, they know this, that one learns a lot by reducing mod p with Pisa prime. So that is, we're going to work over finite fields. So finite fields are fields that have a finite number of elements, and they're classified by this number here. So p to the k, p is the prime, k is a positive integer, and this is the field with p to the k elements. So I won't assume that you are, some of you, of course, will be the experts on this, but I'm assuming everybody knows what this is. So a field, so a brief introduction to field theory, right? So a field is a set of numbers with two operations, the addition and multiplication, if you like. So that F is an abelian group with respect to the addition, and F minus the additive neutral is an abelian group with respect to X of the product. So we are very familiar with the complex numbers, the real numbers, the rational numbers. They are all fields. However, the integers aren't. Right? One can also construct extensions, field extension, right? Like, for example, you can extend the rationals by the square root of 2 in this way, right? So this means all the numbers of this form, where A and B are rationals, right? So in fact, it's a field, and in particular, this number, 0, of course, has an inverse, which is given by this formula. So these fields are infinite fields, right? But we're interested in finite fields. So these are fields with a finite number of elements. The simplest one is the field with p elements, right? And you can think of that as the field of integers mod p. So not that p needs to be a prime, otherwise not a field. For example, the integers mod 6 is not a field, because 2 times 3 is 0, and 0 have inverses. So this is an example, illustration of F7, the field with 7 elements, the inverses, and then the squares of each element. And notice that only the 0, 1, 2, and 4 are squares, not 7, of course. But 3, 5, and 7 are not. So you can consider extending this fundamental field by objects, for example, that are not squares. So, for example, the field with 49 elements here, right, is the extension by the square root of 3, right, of F7. It's a quadratic extension. But more generally, FQ, right, is the field with Q elements, And as I said before, they are classified. This is a well-known story from the field. So there are fun facts that one uses when one is working with finite fields, right? For fields of characteristic P. So consider the Fermat theorem, right? Take an integer and take the power of c to the p is a prime. Then you can prove that that equals the number c mod p. You can prove that by induction. So in Fp, c to the p equals c mod p. And in Fq, you can extend this to Fq, and c to the q is c. And then there is another fun fact, right? That if you take two elements in Fq, then a plus b to the p, right, is a to the p plus b to the p, and then all the intermediate terms have a p in front of them. So they drop out, right? Mod p, this is the answer. Perfect. So now let's consider an algebraic variety defined by this generic polynomial with coefficients in Fp, right? And let's take the x's to be some large algebraic closure of Fp. So one can show that if you start with your polynomial, the set of solutions, you have an algebraic variety defined by the set of solutions of that equation, then you can, then that implies that p to the power p is 0, 2. But by this little fun fact that I told you before, that means that this implies that the polynomial evaluated of x to the p is also 0. Right? So x to the p satisfies the same equation as x. So this map that sends each coordinate x to the p is called the Frobenius map. So this map, what this says is that this map is an automorphism of your algebraic variety in the finite field, and the fixed points, right, those that satisfy this condition, are precisely the points, the points over Fp, right? That's because of the previous slide. So the number of points that you want to count is the cardinality of this set, or the cardinality of this algebraic variety defined over P, right? It's the number of solutions, and that is the number of fixed points over Fp, fixed points of the Frobenius, right? So more generally, you can do this over Fq too, right? But I just wanted to illustrate this for Fp, right? And of course, if you do this on a case-by-case basis, you see that this depends on the number of the parameters, right? Or if you change the parameters on the derivative website, you'll get different number of points for solution. So let's return to the algebraic variety that we had before, defined by a polynomial with a coefficient 5. And now let's take phi to be in Fp. So the fundamental quantities of interest will be this number of points, right? With the number of solutions of this polynomial over Fq, right? There is a generalizing function for this number, for these numbers, which is called the zeta function. So this is the zeta function I mentioned before. And it's defined by this equation. This is the exponential over the sum of this. The exponent is the sum that contains the number of points. This is a formal variable, right? And of course, this is the local zeta function. That is, you compute the point p, right? This should be NQ, right? It's a factor. And of course, that depends on both p and phi. Now, this was the subject of a whole magnificent mathematics in last century, right? Called the right conjecture. It started with the right conjectures about the properties of this generative function, which then later on became theorems, and then were proven by Turk, Delin, and Grothendieck. So in particular, I won't enunciate all the right conjectures, but I will say in particular that the zeta function is a rational function. That was proven first by Turk. So and this is true even if the variety is singular. So you might have a manifold, a very small manifold, but even if you have singularities, that is true. The other right conjectures are not true for when you have singularities, So for smooth varieties, this rational function, you have a quotient of two polynomials over z, in fact, over the integers, they factorize in this way. So it's into polynomials of certain degree over the integers, right? And the degree of these polynomials is bi, where I is from a Betti number, which is a topological impact of your variety. And I will say more about these Betti numbers later. So yes. So in other words, if you know what the Betti numbers, if you have an derived variety and you know the Betti numbers, you know something about the zeta function. And there is more in these conjectures that I will say. So the simplest case, the variety is a point. That sounds boring to start with, right? So the number of points of Q always be 1, right? So then what happens is that you insert 1 in this exponent. What you get is that the zeta function is 1 over 1 minus t, irrational, still boring, right? But something very good, very interesting happens when you go from this local zeta function to the L series, right? So we enter another concept enters, which is L series. You take the product of all primes of your zeta function when you evaluate at p to the minus s, right? So and then that's just trivially this object here, the product of primes, and this is the Euler product of this series, right? So you take n to be you write down the n in terms of these prime factors, and you can. It's not too hard to prove this. Right? So this is the Riemann zeta function. Right. So you go for something that even for a point, something that looks really rather boring to start with, very decent at the end. Right? So of course now what happens for elliptic curves, and this is again this part of last century work, right? So you have an elliptic curve, you use divine conjectures, and then you prove that the zeta function has that form, right? So the only unknown coefficient is that AP, and AP is related to the point counting over FP, right? So that's it. So as long as P is not a prime of a reduction, that means you don't have a singular variable. So, and the point is that these APs are extremely interesting quantities. They are associated to modular form, right? So this is the modularity theorem that started with being a conjecture by Yama and Shimura that related these APs to modular form. So the proof was a big story by several people, including Biles and Roy and Horner and Diamond and Taylor. And this was proven while trying to prove the Fermat's conjecture. Okay, again, you construct an L function, right? You evaluate T in the same way as we did before. The reason I have it in quotes is that you have to be very careful when your variety is not smooth. You have to add certain factors carefully. And I don't want to enter into those details here, but in the end, you end up with an L series, right, with some coefficients an that are constructed from the APs that we had before. And these are the coefficients of a modular form of the congruence group gamma 0 n, where n is called the conductor of cell to z. So cell to z, these are 2x2 matrices, determinant 1, and integer coefficients, and the congruence subgroup with conductor n is such that the C is 0 mod n. This n is called the conductor, and it tells you about the primes where you have a bad reduction. So this is a definition of a modular form. For those who are not familiar with, is in this context is a holomorphic form. It's a holomorphic function. These are the coefficients that we had before in the L theory. And Q is e to the 2 pi I tau. Tau lives in the upper half plane. So take the plane and take just the imaginary part of tau to be real. Or bigger than 0. So okay, so this is the modularity transformation, right? So that f of the transform by this group of T It gives you back the same function, except for a factor that contains k, which is the weight of the model. This, sorry, this should be W, not W is 2. Okay. So what we want to do today is to discuss this was in the context of Canaria varieties, right? So I see how one count points in terms of units. Are there any questions before I go on? Okay, so now let's switch gears. This is the this was numbered here before. So now geometry. So let me just say before going to the geometry that these questions in geometry are completely unnatural for physicists, right? Because why would you ask this? Right? You consider a polynomial only rational numbers. But it happens that there is a connection here. So Canaria varieties, as I said, we've got these algebraic varieties with certain special properties, right? One is that scalar means that you have a very strong constraint on its metric, that I will discuss this one in detail. And the first chunk class is 0. So that means that if you have these Canaria manifolds, I need a Ricci flat metric. But I will restate this in a different way, actually. Okay, so Canaria manifolds in particular come in families, right? So if you start with a polynomial with coefficients phi, and you deform these coefficients to phi prime, then your variety inside space deforms, right? So these are complex structure parameters, right? These are parameters in C. Yeah, they're the coefficients of your polynomial. And this scalar class that I discussed before, in scalar structure, it has to do with sizes with respect to metric. So one of them is the actual size of the manifold with respect to metric. But the story today won't be about this part. It will be about the complex structure. So of course, having parameters, I mean, these parameters form spaces. These are called moduli spaces, and they have extremely interesting properties geometrically, and they determine most of the physics that we have in certain string theories. So there are very many examples of Canaria manifolds. I mentioned one, which is a elliptic curve, right? You can write a cubic into two-dimensional projective space. So the fact that it's a cubic, that is in fact the fact that the first chunk class is 0. If you take a quintic amplitude, it's not an elliptic curve. It's a homogeneous G curve. So this talk will be about 3 complex dimensions. These are manifolds of 6 real dimensions. For example, this is the most famous one perhaps. You take a quintic into 4. Again, the fact that you take a quintic polynomial means that the first chunk class is 0. So this is an example of a quintic polynomial, right? So the xi's are the coordinates, homogeneous coordinates in 4, and this is the polynomial. The other example that would be interesting that Philip will talk about it is an example constructed by Helena Verrell in 1996, and then discussed some of the elementary properties of this state were discussed by Helena Verrell in 2005, and this is the one that presents very interesting properties for black holes. But there are millions of them, right? Yeah, there's a whole. Oh, what happened here? The wrong thing.
Millions, but finitely many?
Sorry?
Finitely many?
I don't know. Nobody knows.
Okay.
Yes, there are bets all over about how many there are in fact. Yeah. Now we need to have, because to talk about periods, I need the notion of differential forms. So if you have taken courses, if you are a geometer, you are very familiar with what I'm going to say. But if you haven't, then this is an intuitive introduction, a very intuitive introduction. So I'm going to say now that functions are 0 forms. Okay. Then I'm going to tell you what a 1 form is intuitively. So consider a path, right, on the plane or in some higher dimensional space. Then dx will represent an infinitesimal displacement at each point in the curve, tangential to the curve, right? So we're all familiar with integration, right? We're all familiar with integration, right? So if I integrate a function, this is an integral, right? Well, we have all integrals, right? So this here, I'm going to define to be a one form, which is an object we integrate over a one curve. So that's the main important thing, right? So that's a one form. So more generally, a K-form is an object, say omega, that we integrate over K-dimensional spaces. Right? A K-form, so K-dimensional space, gamma. Right? For example, for K equals to 2, we will have an element of area instead that you have at each point. We will have the x and the y, which are tangents to at each point in the surface, like here, and they give you an infinitesimal element of area, oriented area, in fact. So they say that dx, this is called the wedge product, is dx, dy, dx. If you switch this, it gives change by a sign. So that means that the x dx is 0, which is when these two are parallel, you have this area is 0. So that's it. So a two form is an object like this one that you integrate over a two-dimensional space. So a K form, I can write it in this way. The 1 over K factorial is just it should be n factorial. So there's another type of that. 1 over n factorial is just conventional. Then you have objects in front of all these infinitesimal displacements at a given point, right? So they really determine the tangent space at a point of your space. And this wedge product is antisymmetric. The objects omega m1 to mn are components of the K form. Importantly, so this is a differential K form, right? Something I can integrate over a dimension K surface. So now we define the exterior derivative. We take a form, take the exterior derivative of that, again, I can calculate 1 over m there. So I take derivatives. So this is an operator, right? An operator acting on your form, and the operator takes derivatives over all the variables, right, of omega, and is now a K plus 1 form, right? You have an extra dx there. Notice that the square is 0, right? The square of the square, this operator squares to 0, right? If you take another derivative, you get two derivatives, but the antisymmetry of the wedge product gives you 0. So it's trivially 0. So then you can define cohomology groups. These cohomology groups are equivalence classes. Say the K cohomology group of K forms, right, that are closed, meaning that the d omega is 0, so they're closed, and that the equivalence classes are formed by forms of two forms that differ by the original one by the d of something, and we call that exact K form, right? So the omega is the d of some other K minus 1 form. The dimension of this group is precisely the K number that appeared earlier in the zeta function, right? So there's a connection there. I mean, of course, reading the proofs of the right projections is a connection between the geometry, right? That's one connection in the zeta function has knowledge of the geometry of the manifold as well. So these are topological invariants. So this is this story. I didn't say that, but secretly I was working on the real manifold, right? But real manifolds are complex, right? So that means that you can always choose complex coordinates, right? On state coordinate patches, right? You have coordinate z and z prime, and in the intersection between two patches, you have a relation between the coordinates, and this expression, the zeta primes are holomorphic functions of the z's. So a coordinate system with a holomorphic transition functions like this is called a complex structure of X. And you think this is simple, that this always exists, and that's not true. Right? This is actually a very complicated question. For example, S2 is complex, S4 is not, S6 is not known, and all the others are not. Right? So it's not due to just interconnecting here you can have a consistent system of complex coordinates. That's not true. So Calabi, because they are complex, then all your K forms decompose into a sum of PQ forms, right? Your P plus Q is K. And notice, so one can illustrate this easily by looking at a one form, right? You have a complex coordinate, say on a two-dimensional space, that is X plus I, Y, right? So then your differential forms, the X and the Y, now become the Z bar, right? So the first term here is a 1-0 form, and the second is a 1 form. So for example, now for a 3 form, you decompose into a 3-0 form, 3 DZs, a 2-1 form with 2 DZs and a DZ bar, and so on. And the operator, the exterior derivative, also decomposes into a del plus del bar, where the del operator takes only derivative with respect to the Z coordinates, right? And sends a PQ form to a P plus 1 Q form. And again, you define complex manifolds. I am not there. For those of you who know complex geometry, you can see that I am being very ambiguous about the difference between a normal complex structure and a complex structure. I don't want to get into those details. I'm talking about complex structures, right? So in this case, these operators, this the bar operator is squared to 0. So you can have cohomology groups, right? There's PQ cohomology groups that are defined by closed forms up to examples. So these are called the Dovol cohomology, and the dimension of these groups is called they're called the Hodge numbers. So now let's go back to Calabi manifold. Right. So what defines a Calabi manifold is this theorem. So there is a unique up to a constant nowhere vanishing 3-0 form that I want to call omega, which is holomorphic. So it's closed, so the omega is 0. In particular, the bar is 0 trivially. Del of omega is 0 trivially, but the bar of omega is 0. So that is holomorphic. So what that means is because it's unique to a constant, the dimension of the 3-0 cohomology group is 1. Right? And that H3 decomposes in the direct sum of the cohomology groups for H0 to 1, 1, 2, and 0, 3. There is a big definition of what a Hodge structure is, but today I want to call this the Hodge structure of the Calabi. So the dimension of H3, of course, is the sum of the Hodge numbers. So H30 is 1, and H03 is 1, 2. And then we are left with these numbers, H21, they are the same. And that counts the number of complex parameters on your manifold. So, so all these are theorems that are not trivial, so I'm just stating them. So you can think of your 3-0 form as defining a vector in a lattice. You take your homology with coefficients, and you have a lattice, and then you have a line inside the lattice that's H20, right? For each complex structure, you can change. I'm saying that there are parameters. You can change the complex structure, and when you change the complex structure, that changes what you mean by a PQ form. Your PQ form now acquires perhaps a P plus 1 Q form too, right? So when you vary the complex structure, the way one studies the variation of the Hodge structure is by studying how this omega moves inside H3, right? So these are variations of Hodge structure, right? And as I said, this H21 is the complex dimension of the moduli. questions?
You only have one. So what happened when you actually degenerate the family to going? What can if I go to infinity, for example? So what happened with the Hodge structure? So you need actually to.
Okay, so yes, so there are degenerate cases. So you have a nice modular space for the complex structure, except at that point something happens, right? Your manifold might become singular, right? Or there are these large complex structure limit, that these are a horrible degeneration, but not so horrible, in fact. Yes, so at those points, something happens to your whole structure. Right?
But you don't want to consider these cases, right? Or
not today.
Not today.
I have a bit to say about them, but not today. I'll say something about one of the cases.
Okay.
Well, this is a very interesting question because that's how you need to understand that to determine really the modular space properly. So what are periods? So a canonical way so there is a canonical way to give coordinates on the space of complex structure, right? So and that is to study the variations of the complex structure by studying how omega moves inside H3. So the coordinates of that line moving inside H3, those are the periods. At least the periods we are going to discuss today. So in other words, you can write down omega, right, as a sum on a basis of three forms. This is a basis of 3 forms, and the coefficients here are the periods, right? Now you integrate your 3 form. So a 3 form, one that you integrate over a 3-dimensional subspace. This is a 3 cycle. The fact that this is closed means that these are cycles, have no boundary, and then this gives you the periods. Right. So this is a basis of the dual, the Poincare dual homology. Right? So, but this is what matters to us.
So periods are maps that so the domain of these maps would be the H3 or
sorry?
No, the domain of these maps would be the components, the Hodge components, and they choose coefficients. So they take.
They're just literally the coefficients in that. Yeah.
Yeah.
Yeah. So.
Yeah. And the structure of those
numbers.
No
numbers. The periods are numbers, no maps.
No. Well, okay.
But they're
But they're integrals.
I would say more what they are. You can, if you can construct this form, like in some cases you can explicitly construct this 3 form, and if you can find your basis of cycles, what you get end up is a series. I feel as an example. But that's for a given complex structure, these are numbers.
Yeah, for yeah.
For a fixed complex
yeah.
Yeah. This omega is parallel with respect to the each beta connection.
Yes. No. For Caladios, yes. Exactly. Yes. See, for Caladian manifolds, this is parallel with respect to the yes. That's right.
And if I change the metric or I change the connection, this number may be changed.
So okay. So this is a story that how will you construct parallel transport from your modular space? That's more or less the right. So and then this is the story of that I mentioned before of this geometry on the modular spaces. So there is always a connection on this space that is flat, in fact. And this is called special geometry. Right. So and one can explicitly construct this connection, in fact. So in an old paper with Philip, that's called modular space, we actually do these constructions. Yeah, it's a very good question actually. I mean, this is how you build your modular space. Yeah. So this goes to, and this is also related to periods, right? They determine the geometry of the modular space. The geometry associated to this is called special geometry, and in codes, there's a dictionary between that and physics. So, but what we will see today is that they have arithmetic content. they're also calculable, at least to some extent. I mean, they satisfy differential equation, the properties. It's called the Cartwright's equation. And for a one parameter example, meaning h21 is 1, right? And p3 is 4. For one parameter examples, this operator is of degree 4. And but generally, there is a prescription to obtain the Cartwright's equation originated by Dwork and then Griffiths and then Kaplanov and Televinsky. Prescription to do this, and it's not easy, right? In general, this is fine. Right, so this is for a one parameter family. So the degree of this polynomial is 4, because I have h21 is just one parameter, one complex factor parameter, h21 is 1. And one can find, for examples, one can find the differential equation and solve it around singularity. So this Cartwright's equation has certain properties, as I said, in particular has regular singularities. So one such regular singularity is called the maximum important monodromy point, which I won't get into that today, but for many canarians, the generations of the one Alex was asking before, in which your threefold, your three-dimensional manifold, degenerates into basically a vibration of a three torus over a three sphere, right? So that happens at this point that I'm going to define to be quite as 0. And then when you write down your solutions, you get periods. The solutions are series. So this one, there is a holomorphic period, there's a fundamental period equals to 1 as opposed to 0. And then there are logarithmic solutions. And these F's are regular series. They're all regular series. These solutions are found using the method of Venus, right? To find logarithmic solutions for those of you what happened here. I have something. Something happened here. I will go on here. No. But I don't know here. I don't want to touch anything. Thank you. Okay, good. Thank you. Okay. So for the quintic, right? So one can compute this. We put this differential equation and for the quintic, one can complete this differential equation, right? And in particular, one can the fundamental period, right? This holomorphic period has this very nice form, right? Where the coefficients have this form, right? In factorial or in factorial to the fifth. And the differential equation has three regular singularities, the Mon point, but there are others, right? That we won't discuss today. Conical means ordinary double point singularity. So the Hule-Campbell example that we will discuss later the differential equation has 5 singular regular singularities, but it has one a Mon point, which is the one that's relevant for the discussions today. Any questions? Now I want to put all this together. So let's go back to zeta functions, right? And that was the definition, and to the Bank conjectures is a rational function that factorizes. Factorizes in that way, right? So for a calaria, what happens is that B1 and B5 are 0. So R1 and R5 are just 1. Right? We have B3, which for one parameter families, this would be a polynomial of degree 4, the one in the numerator. And in the denominator, you just get factors of the form of this form, right? And this B2 is the second Betti number, which for Calaios is the same as before. So really, the only interesting part, if you like, is the numerator for one parameter family, right? Which is of degree 4. For singular varieties, what happens is that this polynomial degenerates and it has to be smaller than B3. Yeah. Okay, sorry, that is a bit crowded slide, but so this is the right conjectures tells you that RT, which is of degree 4 for one parameter family, depends only on two unknown coefficients, which are related to the number of points, right? In this way, H11 is B2, really, and H and N and NP squared. Those are the only numbers that one needs to compute to determine completely the zeta function. So one needs to count points, right? One needs to find a way of computing A and B. So how do we do that? And how does this vary with phi? And how is the story related to the periods, right? And then, of course, one can go on and ask for properties associated to a series and what's the analog of modular. But this is beyond the scope of the talk today. Okay. Yes. So, of course, there are different ways of computing these numbers. I'm going to discuss one. Philip will discuss another one called the deformation method. So we are just going to count points. So we're going to start with an exercise, with a very simple exercise. I want to start by counting points mod p, right? Of course, you want the exact number, not just mod p, but this is a very good exercise, in fact. So let's recall the Fermat's-Liu theorem. It says that h to the p is a mod p, right, for an integer. So now you can write this as a to the p minus a equals 0 mod p, and then you can factorize an a here, right? This a times a to the p minus 1 or 0, which means that a to the p minus 1 is either 1 mod p when a equals 0 or 0 when a is 0, right? So let's take now your favorite polynomial, a direct variety, the final polynomial, and consider this object 1 minus the polynomial to the power p minus 1. So if for a given x, the polynomial vanishes, right? Then this is 0, and then you get 1. You get number 1, right? If for a given x, the polynomial is not 0, then p to the p minus 1, p by this here, is 1, right? So you get 1 minus 1, you get 0. So this object is telling you when you have a solution. First, why is this jumping? Anyway, so okay. So the number of points now you sum over all your points in FP. The end you have in coordinates is precisely this object, right? Mod p, of course. So this was done a long time ago. This was written out a long time ago in 1935 by Chevalier and Warning. But then this is when we saw this kind of counting, we saw it for the acuity, for the elliptic curve, in fact, originally. We started working with a number of theories, Fernando Rodriguez Villegas, and we ended up writing formulas, exact formulas, opposed to just mod p. And recently I saw Eric Panzer and Francis Brown using point counts in the context of amplitudes in physics, which is, again, the story for another seminar. So for the quintic, if you take your quintic polynomial, the one we had before, right? I say you take your favorite polynomial, I say at the moment is the quintic. So we expand this expression here, right? We expand this using the polynomial expansion as usual. And then you use the fact that if you sum a to the n when there is a p, you get either 0 or minus 1, right? Because they subtract a to the p plus a. Right? So you get 0 when p minus 1 doesn't divide n, and minus 1 or p minus 1 when p minus 1 divides n. So then after some literally a page of computation, you end up with this formula for the quintic. But you remember, this is the fundamental period of the quintic, right? The one that we have AM. I think I have it. Let me go back because it's worth looking at this again, right? So there, right, for the quintic, there, the fundamental period is this AM pi to the n. to the n, where am's are by m factorial or m factorial to the p. Right, so what you get here is not exactly the period, is a truncated period, right? Truncated to the first few terms, in fact, the integer part of period 5. So this is the first notion why you get, why are you getting a relation between periods and this point counting? You see even more p, right? And this you take any hypersurface in toric varieties, which is a very way to construct parameter manifolds, and even with more parameters, you end up with a number of points more p being related to this fundamental theory. Right? So the reason behind this has to do with, we discussed before the Frobenius automorphism, right? So this has to do with an application, again, buried in the proof of the Dirac conjectures, the use of the extension of the Lesch's 6-point theorem from topology to a p-adic version of this, where you use precisely the fact that the Frobenius for using an automorphism. Right? So you use the Lesch's you take the Lesch's theorem from topology, and you do something actually rather complicated because you have to work on the other place. And then your point count is related to what's called the traces of Frobenius, right? Where this F here is a linear map induced from the Frobenius on the homology or cohomology of your manifold, right? But these cohomologies are these entire cohomologies that are beyond again the scope of this talk, right? So it is that's the intuitive reason, because you are relating the number of points to the action of the Frobenius of the, say, the third cohomology for polynomial R, and of course those are related to the periods as we just discussed. Yeah. So that's we get an intuition as to why, or why can you write down an exact formula, right? We want to do this exactly, right? And we want to have formulas in terms of parameters. So it goes as far as I mean, of course, probably more references. I mean, it's a large bibliography on this. Perhaps started with Gusa in 1958, where classification curves. Of course, Dwork did a lot of work himself in the 60s. So then more and more papers. So the work that we did for the 20 was in 2004. And then there are people like Boykers and Lashenko and Marquet who are working precisely on this and the relation to the port structure. And now we have this work with Eleonora, where we're writing these more explicit formulas in terms of the periods. So we don't have the time, or I mean, to show you precisely how to do this, because it requires p-adic analysis, basically. So I will just give you an answer, right? So actually, before I go to the exact, are there any questions about what I said? Yeah.
I have a question. So I know you don't want to talk about mirror symmetry, but when you talk about periods,
I always want to talk about symmetry.
Okay, good. When you talk about periods, so I just think of the Gromov-Witten invariance from the other side.
Yes.
Right? So what will be the interpretations of the A model interpretation of this counting? Because this counting is purely B model thing, right? So is there any A model interpretation for the counting? Or
I don't have a one-line answer for this at all, right? So I don't know whether Peter wants to mention something about this, but there are computations there. So the A and B models, and we come from string type to A and type to B string. Any computation that you do here has a mirror, right? By the mirror map, always, right? So if you take the zeta function, what's the zeta function of the mirror? The zeta function doesn't know about mirror symmetry because it only encodes the complex structure parameters.
So you know nothing about the Keller or something.
Well, it knows how many there are because it knows about P2. Right?
But not how to.
But it doesn't have any Taylor class parameters there because Taylor class parameters are not algebraic. Right. So the classical zeta function is not the right place for this, I think. Right. So of course you can now construct the zeta function for the mirror, and you can say, well, the complex structure parameters here are algebraic, and they are the Keller class parameters by mirror symmetry of the other one. Okay, so that's almost the best I can do. I mean, construct both sides. Yeah. Yeah.
This mirror map translation, let's say, is canonical, or I mean, there is a precise way to pass.
A physicist says yes.
Okay.
I know I could sit down with you for half an hour and tell you how to get it. But if you are a mathematician, you define it, which is to me is horrible. But that's the way you have to do it. Correct me if I am wrong.
Yeah.
A mathematician just defines a neural map, whereas a physicist deduces it from the thing. I mean, there are very beautiful things some mathematicians have done with mirror symmetry now, but that is a point that is not clear how a mathematician will conceive of that.
Okay.
Begin. I mean, it has to do with the fact that the physicist says on this side I don't have quantum corrections, and on this side I do have quantum corrections. It's that kind of story that is very difficult to put in a mathematical context.
Yes, that is my question, because you have the zero function here, but how do you say that is the precise zero function in the other side?
You have to write
one.
down an arithmetic version of the mirror map, and I don't know how to do that.
Okay.
I just don't know. I mean, I have a mirror map, and using a manifold, and I say, in a mirror, I'll tell you what the mirror map is. And then if we talk about the zeta functions, then I don't know, because the mirror map is the mirror map. So this is interesting. So I can be carried away.
Yeah. Sonia.
So the mirror map is this. So mirror symmetry tells you that the morphism.
No. Tal vez tienes que presionarlo, no sé. ¿No sabes la presión? Sí.
No, es como amarillo. Entonces,
Eso es lo que toca presionar, ¿no? No, siempre que toca quitarle.
No, desde la
voy a quitarle, creo. Es que hay que presionarlo contra la altura.
Presionando esto y sorry. Yeah, I mean, you have to wait.
La cinta va bajando. Será amarillo.
Solo presionarlo, ¿no?
Solo presionarlo.
Solo presionarlo muchas veces. En la punta hacia abajo baja más rápido.
Sí. No, pero ya acá de prestar el número, ya.
One cycle has the modular space of complex structures, and this is the special geometry. And the same parameters here for phi, right? And on the other side, so this is for a palladial X, the complex structure phi, and here you have the mirror, like X with parameter T, right? And you have the modular space of the Keller class parameter, complexified Keller class parameter. So T. So this here means that the mirror symmetry tells you that these are isomorphic. And the isomorphism map is called the mirror map, right? And the mirror map is this map in T. But when you write it down, I don't have a slide. Oh, it's not here. If you write it down, what you get is a series. It's a series. It's fine because I can't remember. For the quintic, you get a series with integer coefficients, and Q the M, where Q is e to the 2 pi I t. So this is the form of these are integers. So, and the mirror map is really a ratio, a rational function of periods. Right, so that's how. So I know the arithmetic content of the periods, and for the life of me, I haven't been able to translate this into the zeta function. And the problem is this cube. That's why I don't know how to interpret that. Well, that was the question, I think, or related to this.
I think it was related.
Sorry?
Not related. Because he wanted to know how canonical it is. But
Well,
this is just the ratio of the period.
this here is a ratio.
But this is the ratio of the period.
It's a ratio of periods.
It depends on the ratio.
Right. So I think if I don't remember explicitly, something like 2 pi IT is the first logarithmic period over the holomorphic period. For the quintic, for a one-parameter family, this is how it is. Right? Yeah. So the other question is, why are these integers? Nobody knows. Okay, so it is a definite number, and we seek to complete it exactly, and we can expand. Of course, then we do expand this in powers of p. Well, we know how to compute the mod p, but then you want to compute mod p squared and mod p cubed and so on, right? Where there's an n missing here, where n, these n's are numbers between 0 and -1. If you want to evaluate mod p squared, mod p cubed, and so on. So this leads naturally to periodic analysis. So what we did is to take from the work of Dwork, that in the periodic context constructed a character, and we use this character in terms of Gaussons and analogs of periodic gamma functions and so on. It's a long story, very pretty but very technical, that I cannot get into that. And then you get a series, right, that contains all this. Remember these regular series in the solutions are these f's here, right? So there are a number of things that I haven't defined in this formula. So this phi in square brackets is called the Teichmüller representative of phi, which is again is a periodic number, right, that satisfies Teichmüller phi to the t is Teichmüller phi, and it's the unique one that mod p reproduces f in phi in fp. Right? But it's the object, when you think about it, therefore it's the object that is natural for this point counting, right? That is, if you have phi that is in fp, you want your counting to be invariant under changes of phi by something that is for the p and so on. And then you convince yourself that is this object that appears, this representation of your parameter that appears in the point counting. So the fk's are the regular series appearing in the periods for k equals to 0, 1, 2, 3. We had only 4 periods, right? Because B3 is 4 in a one parameter case. But you have here all the way to infinity. So these we are calling the semi-periods. Take a moment what they are. So these are the periods, the periods, these are the regular series that appear there. And then the periods, of course, are obtained from the Frobenius method to finding logarithmic solutions of the differential equation. But where you propose a new period, if you like, with coefficients, capital A, that now have a dependent on the variable epsilon, and we have now 5 to the m plus epsilon. And then when you start taking derivatives of these, you start getting the logarithmic solution. Derivatives with respect to epsilon, you start getting the logarithmic solutions. But of course, these A's are not random. At epsilon equals to 0, they have to reproduce the AMs that you had before for the periods, right? So these Frobenius periods at epsilon equals to 0 needs to give you 5, 0, right? So this is effectively this. And then we choose a particular basis where A with M is 0 of epsilon is 1. right? And then the differential equation, the Picard-Fox equation acting on this Frobenius period doesn't give you 0, gives you something on the right-hand side. So the semi-periods are the higher solutions that appear in this equation and obtained by taking further higher and higher order derivatives of this Frobenius period. Right. So let me go back to the formula, right? So this series represent, as before, as was the case of P, these are truncated series, right, to the first P minus 1 terms. And then this notation, this is the truncated series, this K here means K derivative of the truncated period, right, with respect to the parameter. And this H comes from our choice of basis, right? It can be expanded in powers of epsilon, and it happens to be given in terms of the periodic gamma function, as opposed to just gamma epsilon. So that's the punchline for the quintic, right? So you have, so expanding it better, you have in the big brackets, you have a series of periods, or semi-periods, and then you have, in the second line, you have some coefficient, and then the third derivative of the thing in brackets, and so on. So that's the structure of this, and what transpires is that this is very general. So these H's, these coefficients, we can compute. I mean, they are given by this periodic zeta function, evaluated at 3, 5, and all integers. And we are trying to understand what these numbers are. But we know, for example, this one, we can prove that this is related to the Euler number of the variety divided by some, what the physicists before like Karl problem, which is really a triple intersection number. So this is just for completeness the definition of the periodic gamma function. We don't need the details. Don't focus too much on the details at the moment. I mean, it's just that. I mean, what's important is this thing, this series here. Right? That you have an operator acting on your periods and semi-periods. And so the role of the semi-periods, this is something that we are investigating, right? And P for the quintic has to be smaller than P to the 4th. And so we have found interesting cancellations and congruences between the semi-periods that we're investigating. And this is the punchline, right? That's it. So this is for the example that Philip will discuss. And as you can see, the formula, so this is the number of points. It has factors that depend on the Q. And this is, well, we're calling this the primitive part of the point counting. And this is another example, and the form of the series there is the same. The periodic series is completely analogous. So basically what we're working on is to write down the number of points. If you give me a variety and you give me its periods, I can conjecture what the number of points is at the moment. And I call it a conjecture because we only have done this for many examples with proof, right? And we are trying to see how the more general conjecture can be proven. So we could continue exploring these formulas. We are discussing what happens with varieties that are not Calabi-Yauss. I mean, and of course, Philip will tell you later an arithmetic strategy. If you study the arithmetic, you have questions about the Hodge structure of the manifold. You can use the arithmetic to study the Hodge structure. Thank you very much.
So we are kind of, showing time, so we can discuss during the break. So we have a break, 20-minute break. So we resume at 11:35. But we can discuss with Sonia. No, dale, no, dale.
Sí, porque era igual. Sí, pero
Siete y media, claro. Empezaban
a las 9. Se recogía a las 8 y nos quedamos a 8 chicas, salimos con menos digamos, el problema que uno es ahora logrado, sería obviamente, ¿no? Pero los logrados reacomodar,
pues quizá ese día no va a
pero yo sí tenía donde estaban los estudiantes.
no, y ya los nervios de que eso esté antes de está haciendo cosas que no se quedaba ahí.
No, nos quedamos allí, hicieron, bajaron de nuevo al pero se quedó ahí por la puerta de nosotros. Nos cambiaron. La mayoría se quedó. Entonces quedó en los pasillos, había unos rapadones bonitos. Entonces cayó en el ascensor, está todo bonito. No, era pánico, ¿eh? Un ascensor se dañó, los otros y aquí están los ascensores. Entonces esto impide. Entonces voy a ver aquí está la posición. Estamos arriba, corrimos, hicimos así y eso se movía. Y esto se movía. Sí, es como yo lo veo. Ese claro, porque es que a los padres le colocan. Sí, pero cuando le pongo los partes de los padres. Yo veo estas variedades como del sensor. Eso traccionado. Como si fuese rata, descubrimos hasta aquí. Y apenas ya se calmó, ya nos abrieron aquí, pasamos por el hall. Sí, o sea, cambian algo de estructura que yo le doy a partir de Calabria. Bien, sería que era mampostería, que lo que la interpretación. Ya salimos de aquí afuera. Luego la sala entramos a comer otra vez. Claro, porque estábamos en cuanto es muy parecido a las colmenas. De pronto le entiendo. Se le cayó como de la pelista. Pero eso fue el vez. Ese efecto estuvo bastante bien. Porque vemos que era la 100. Métrica era con 52. Sí, pero muevo solamente la sala. Y el complejo lo hace. Y los edificios es que en casi una cuadra, donde abajo es un parqueadero. El primer piso no tiene un piso. Los carros, pues desaparecieron. De todas maneras, ok. Yo todo el edificio así.
Partidos, sí, justamente.
Y las paredes se conservan, o sea,
Y cuando haces deformaciones infinitesimales de
pero
los
de adelante, o sea, solo las cosas de abajo.
eso es
Usted analizamos, claro, nos pasa así, claro,
Sí, sí,
pero
sí.
varios, con una cuadra.
sigue haciendo.
Ustedes como lo hacen, ¿no? Ustedes parqueaderos.
Sí, sí, sí.
No, el parqueadero desaparecieron los carros. Muchos
Lo
de
que
ellos
te das cuenta es que cierto tipo
duraron
de
otras actividades. Porque no eran delgados, eran muy gruesos.
se separa de las de otro tipo de.
Pues es como cuando llaman, me parece.
No, claro, claro, sí, 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 sí. Y eso que se conocen de las grandes ciudades, pero municipios aledaños hasta ahora, terrible. Porque hay una señora que cuida a su madre y mandó un video, no pudo ir. Pues se viajó para allá, porque la familia no se
Entonces,
comunicaba.
las deformaciones
Lo Restrepo, así, Restrepo aquí, y otros por ahí. Ella decía, el fin de semana llegó y ya no sé por qué. Totalmente. Claro que la frase bonita ahí.
Pero cuando dices de la estructura, ¿cuál es la relación?
No se perdieron,
Pero la mayoría de
Y
las
eso
casas
por eso un campo de turismo, algo así. O sea, esa información,
no,
eso infinitesimal puede ser,
no, en la canal no.
Ah,
El P1 es el.
la hermana de él
Hay un canal, los canales que son.
era la novia de un amigo y estamos
Sí,
pero
aparte de eso,
a llegar
sí, creo que sí.
era una parte de la familia de mí, pues, como 5 años,
muchas gracias.
gracias vacaciones,
Sí, dentro de todas esas noticias, la de esta periodista.
la sobrinita. Mi hija sobrinita era la hija de nuestra amiga. Muy triste. Pero bueno, ella tenía que estudiar, trabajar, entonces estaba cerca de la trabajo. La única va a cuidar a la niña, y ese muchacho que eran 3 habitaciones grandes, grandes, y atrás estaba el baño, y allá se metieron los 3. Al menos el señor se va abrazando a la niña. Es decir, no, que se me la dio así, no. Todo empiezo con una piscina arriba, pero no se sabe cómo.
Ay, Dios santo, sí. Ay, lo siento y entiendo, sí nos acordamos.
No, resulta tan berraco.
Sí,
Sí, pero bueno, logramos el evento logró terminarse. El evento logró terminarse con esas variaciones, es decir, que quería irse rápido, entonces le daba la clase rápido. No, la verdad, no. Tuvo dar el
Profe, ¿cómo está? ¿Cómo se encuentra? Muchas gracias por la charla. Profe, ¿cómo inició pues, el estudio? Pues, no sé, cómo se interacción entre física y matemática y tanto le gustó. Sí. Bueno, sí, en ese momento, para empezar a estudiar, es como que le llamó la atención, como esa motivación que se me dio. ¿Cómo fue la motivación? Pero creo que, bueno, es mi ignorancia. Es más fácil desde matemáticas porque acá tenemos definiciones.
Esa es una. Algo matemático
Creo que allá hay más conjeturas que acá.
Sí,
Bueno. Profe, otra cosita. Bueno, yo no sé nada de teoría de cuerdas. No sé mi ignorancia también. Sí mencionó, no vi como el sabor de teoría de cuerdas. Sí. En la próxima, en la segunda parte. Y su compañero va a hacer la otra parte, que es la de la relación.
puede ser matemático, para nosotros primero nos apareció en la teoría, te das cuenta que son solamente con mi familia. La definición de masa, de otra estructura que tiene la teoría. Yo creo que pero también matemáticas que lo usas para entender cosas.
Podría llegar a cosas que no tendría. Está acá, el profe, apenas pusieron el agua. Acabo de preguntar. Profe, listo, yo le comento algo. ¿Sabe yo qué pienso? Bueno, acerca de la conjetura de, bueno, la hipótesis de Riemann. Yo pienso que hay un argumento probabilístico para probar. Es bonito, mi cabeza. Digamos, le comento, yo soy estudiante de estadística, pero hago parte del departamento de matemáticas. Y usted empezaba a mostrar esos productos de las funciones y decía, eso es una función de verosimilitud. Y luego llegaba la función citada no tiene sentido. Entonces, y otra preguntita, ¿cuántas horas estudiaba al día? Porque cuando era estudiante. Como me decía la otra vista desde el cuarto. Dinámico. Gracias.
Bastante simple, o sea, y paso ok. Sí, ok. Sí, ese pedacito. Y yo porque yo estaba pensando en eso y no,
Yo solo hice comentarios.
Sí, 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 sí,
Realmente un minuto.
¿Cómo estás? Excelente. Básicamente ya me acabo de hacer.
¿Qué has estudiado? ¿Qué has estudiado hasta ahora?
Yo sé cómo es. Creo que todo se presenta la carrera. Bueno, la respuesta ya como que es un tema área de la computación.
Sí, ¿Tú qué quieres estudiar?
Se recuerda lo de lo que creo que es muy importante.
Gracias. Está el nombre de la persona se va a pasar.
Si te gustan las dos.
Es que cuando ya mostraba las funciones de la funcioncita y luego llegaba la funcioncita de rima, decía, profe, ya le comentó a yo fui eso que hay un argumento probabilístico para probar la función de rima. Y ella me decía, ay, sí, no, esto es muchas a mí siempre me muchísimo que hacen cuántas horas de eso. Decía acá, 8 horas que regular, 8 horas, 11 horas, la mañana 4 horas, y ay, yo todavía es una mala. Los estudiantes de Cambridge, entonces, 8 horas mínimo. Por eso es que lo tomamos.
Sí, uno puede solo concentrarse. Por ejemplo, nosotros tenemos
Suma que
Ya tienes aquí. Sí. Okay, so we will start the second talk of this morning. So it's really my pleasure to introduce Philip Candelas from University of Oxford. Es un placer presentar a Philip. de la Universidad de Oxford. So we will continue Xenia's talk, and she will talk about black holes and the arithmetic of family of Calabi-Yau varieties, connection between number theory and physics, part 2. So please, Philip.
So first, let me say, of course, it's a great pleasure to be here in Bogota for many reasons, but also a distinct honor to be asked to take part in the celebration of the 70th anniversary of the mathematics. What I'm going to talk about is joint work with Xenia, with Dulko van Straten, and students or former students, so Mohamed Elmi, Puru Kusala, and Joseph McGovern. So we'll touch on work done with all of them as we go. Okay, so let's jump into the deep end. So this talk is supposed to bring together number theory and physics, show that number theory has something to say in physics, perhaps physics has something to say about number theory. And we're going to jump in, and I'm going to sort of give you a sort of a one slide or talk about black holes while standing on one leg. Okay, so what's a black hole? Well, first of all, let's consider a spherically symmetric black hole. A spherically symmetric black hole is a spherically symmetric gravitational configuration where the mass has shrunk down to, in some sense, zero size. So there's something going on. This is supposed to be a plane. This is going to be the horizon. This circle here is the horizon, and I want to explain the concept of a. So if the sun were a black hole, then there would be no daylight, but we would continue to orbit around the sun in the same way that we orbit around now. The mass would be the same, the gravitational attraction would be the same. But of course, if the sun was shrunk down to zero in size, you could get very close. And as you get very close, the gravitational field gets very strong. And there comes a point where light cannot escape. And that's the boundary between the region where light can escape from the center and the outside region where light can escape to infinity is the horizon. I'm going to try and explain that. So suppose you are an observer a long way from the black hole, and that's you, that's this dot here. And you emit a flash of light. Then a millionth of a second later, that flash of light is described by a spherical wavefront centered on the point of emission. Okay, so that much is easy. But as you get nearer to the central mass, that changes. So here, the observer emits a flash of light, and a millionth of a second later, it describes a wavefront that's roughly spherical. It's actually slightly elliptical. It's slightly elliptical, and it's no longer centered on the observer because the light, if you like, is attracted to the black hole. So the observer no longer finds himself in the center of this proximate sphere. And as you get nearer to the black hole, this gets more and more extreme. So the light, if you like, falls towards the hole. And there comes a point where you emit a flash of light, and a millionth of a second later, it forms a surface, but you're no longer inside the surface, or the point of emission is on the tangent to this surface, is on the boundary of this surface. And then the locus of that, if everything is spherically symmetric, is a sphere, and that's the horizon. It's the point from which light no longer, you see, if once you're here, light that you emit goes in, and there's no longer the possibility of communicating with infinity. Okay, so that's a sort of 30-second introduction to what a black hole is, and as the point I want to convey is that there's a horizon. The horizon itself is not singular. So relativity is a theory of gravity. It's also a theory of geometry. It's also a geometrical theory. And space-time is represented by a manifold. And the manifold isn't singular on the horizon. Nothing, so to speak, singular happens. Nothing infinite happens on the horizon. Something does happen inside, but that's separate from the horizon. And so we will talk about horizons in a minute. More about horizons. Oh, so now we're going to think in 10 dimensions. So the previous caricature was a sort of 4-dimensional picture, the 4 dimensions we know and love. And now we think in terms of string theory. And in a certain way of thinking of string theory, space is 10-dimensional. 4 of the dimensions are the dimensions we know and love. And another 6 of the dimensions are taken up by a Calabi-Yau threefold. And the Calabi-Yau threefold depends on parameters, and our model of space-time is not the usual one that you take. The usual one you take is that you consider Minkowski space, at least a particle physicist does. You consider Minkowski space, and you attach to each point of space-time, you attach a Calabi-Yau manifold, and you attach the same Calabi-Yau manifold. So if the manifold has parameters, then the parameter values are the same at each point in the 4 space. And now we're going to allow the parameters to vary as you move around in the 4 space. And since everything is spherically, we're going to assume everything is spherically symmetric, and then the only thing that counts is the radius. And so really, we're going to think of Calabi-Yau manifolds fibered over a line. Okay, and so what that means is you have a Calabi-Yau manifold. It has parameters, and the parameters, if you like, are the radius, or the parameters are functions of the radius. So at infinity, there's some Calabi-Yau manifold. At infinity, of course, you're supposed to be allowed any Calabi-Yau manifold, because at infinity, you're a long way from the black hole. You don't care about the black hole. So you're allowed any manifold. And then as you come in, the parameters change. You give the parameter infinity, but as you come in, the parameter evolves in R. And at the horizon, so this is the horizon, then the parameter assumes a value that we could call phi 0, but we're going to call phi star. And then I'm doing something which is that the radial coordinate I'm calling R, but it's not, I mean, it's a radial coordinate. You can choose the radial coordinate in many ways. And one way of choosing the radial coordinate is that the horizon occurs at R equals 0. But R equals 0 isn't the singularity. The singularity is over here somewhere on the other side of the horizon. That's some negative value. And you can write a spherically symmetric metric in terms of one function, u of r, and it has the form ds squared is minus e to the minus 2 u of r dt squared plus e to the 2 u of r dx squared. Dx squared is x, y, z, the 3 spatial coordinates. And u of r is such that at infinity, u is 0. So this part of the metric just becomes dx squared, and this becomes minus dt squared plus dx squared, just the ordinary flat metric. And at u of 0 at the horizon with these coordinates, what happens is the coefficient of the dt squared term vanishes. Now, there's a system of equations. If I demand that this is a solution of supergravity. So supergravity is a generalization of gravity, contains also other fields. It contains also a certain number of copies of electromagnetism. So in fact, the number of copies it contains depends on the Calabi-Yau manifold, and it contains H21 plus 1 copies of H21 is the, no?
Times 2.
Times 2, 2H21 plus 2. Yes, okay, 2H21 plus 2 copies B3. Right. The third Betti number contains B3 copies of electromagnetism. There are B3 charges, P's and Q's, so they can be electric and magnetic charges. Okay. And then there's a system of differential equations. So you choose yet another radial coordinate. So rho is 1 over r to write the equations in a more or less neat way. And there are equations, there's a differential equation, a system called the attractor equations that gives you how u depends on r, or u depends on rho and phi depends on rho. And I just point out what these various things are. G is the metric on the moduli space. So it's a Kähler metric, it's the second derivative of Kähler potential. The Kähler potential is given by the integral of omega, which omega bar. Omega is the holomorphic 3 form, which was so prominent in Zenit's talk. And then Z, the quantity that appears here, is a central charge, a function of R, and it's given by, it depends on a cycle gamma. So it depends on a period. This integral of omega here is a period. And so you form this period, you multiply by an exponential of the Kähler potential, and you have Z. And the only thing I haven't told you is that G with the indices up is the inverse 1 over G with the indices down. Okay, so the details of this are not important, except that there is a system that you can write down. System of equations that tells you how the metric evolves and how the Calabi-Yau manifold evolves, because the Calabi-Yau manifold depends on phi, phi depends on r through these equations. And before we go on to the next slide, let's just go back to that one then and write in something. So there's a puzzle, and it has to do with why this is called the attractor system. And that is that at infinity, you have a certain value of the parameter, which can be anything. And at the horizon, the parameter has to be something special, because the boundary condition, or the boundary consideration, so to speak, is that nothing is singular at the horizon. And there's a danger that when you solve these equations, that you find that the horizon is singular. And making the horizon non-singular means that phi at the horizon has to be a particular function, or it has to have particular values, which are determined by the charges of the black hole. So the black hole is a supersymmetric black hole that has charges P and Q, several P's, several Q's. It has charges P and Q. There's a certain phi which is a function of the P and Q, such that a solution exists. okay, with a non-singular geometry on the horizon. And this is hard to achieve. And there's a puzzle because phi at infinity can be anything, but phi at the horizon is determined by the charges. And there's a basic fact in electromagnetism, which is that if you have both electric and magnetic charges, then the charges are integers. So if you have even a single magnetic monopole, then the electromagnetic, then the P's and the Q's are relative integers. So with a choice of units, they're integers. And so how can you have, you know, some phi at the horizon that's determined by integers and a phi at infinity that can be anything? Right? I mean, there are more phi's at infinity, so to speak, than there are phi's determined by the integers. So the way this works is that this differential system of differential equations has the character of an attractor flow. So you get an evolution in R such that interpolates between phi and infinity and phi star. But if you start somewhere else, you could start somewhere else, it would flow to the same, point. So you get what's called an attractor flow in the language of differential equations. And this is something, and this leads to, and the variety x of phi star is then called an attractor variety. Phi is called an attractor point, phi star is called an attractor point. X of phi star is an attractor. So now let's talk about how this plays out, what the geometry of this is. So there was a diagram that Xenia showed you, which shows that you have the space of H3, and you can take, you have the third cohomology, and omega is a 3-0 form, so it defines a line. There's a unique 0 form, 3-0 form up to scale. So it defines a line in this H3. H3 is a big space of dimension B3, the third Betti number. I can only draw 3 of the dimensions, but there are more. But omega is a line, and really is a complex line in that space. But there's a lattice in the space, something that's difficult to draw, is there's a lattice H3 of X and Z, which is the space of charge vectors. So if you have some P's and some Q's, you can choose a symplectic basis . The products being equal. So you can choose a basis of 3 forms, alpha I, beta I over the integers, and you can associate with that a charge vector, which with coefficients that are the magnetic charges and the electric charges of the black hole. And so this gives you an integral lattice in the third cohomology space, corresponding to the the charge vectors. Okay. So if we look at this diagram at the top, which gives us a complex line, but we look at this over the reals, so that the diagram at the top is over the complex numbers, and we have a complex line. So as a real object, the complex line is a two-plane because it's generated by the real part of omega and the imaginary part of omega. So we have a two-plane, and also in this space we have a lattice of objects that we can call which are gamma, the charge vectors, possible charge vectors. And the condition for the horizon to correspond to an attractor variety, so a necessary condition for there to be a non-singular space-time with a space-time with a non-singular horizon is that this object H30 plus H03, which is the blue plane in the diagram. So this is a two-plane, call it V, and it's a two-plane which depends on the complex structure. As you change the parameter phi, what you mean by a 3-0 form and a 0-3 form changes. And so this is a plane parameterized by phi. As you vary the parameter, this blue plane moves around with respect to the lattice. And generally, you ask how does the blue plane interact with the lattice? It passes through the origin, but does it pass through any other lattice points? And in general, of course, it won't. Okay? Unless the slopes are very special, it won't pass through any other lattice points but the origin. And so there's a concept of an attractor of rank 1, which is a rank 1 attractor point is a value phi such that VR of phi contains a lattice point other than the origin. If it, of course, it contains 1, then it contains infinitely many, because it will contain also multiples of that point. Okay, so an attractor point of rank 1 is a value of phi such that this blue plane moves and contains the red vector. Contains some lattice point. And there are supposed to be many of these, although the generic, for a generic phi, it won't be true, but it's believed that at least in some regions of the moduli space, rank 1 attractor points are dense in the moduli space. Okay. It's curious, I believe they're dense. I don't think there's a single example known exclusively. Okay. But of sort of greater interest at the moment is attractor points of rank 2. That's it. Can it happen? It can happen in the dimensions. If we have a one parameter space, then B3 is 4, as we've been told before. And the dimensions are such that you can have a situation where the blue plane actually intersects the lattice in two linearly independent points. They're gamma 1 and gamma 2. So it's something that you would believe never happens, but can happen sometimes. So in that case, the blue plane moves such that there are two linearly independent vectors, gamma 1 and gamma 2 in V, so that VR contains a lattice plane. If it contains two vectors, it contains any linear combination, any integer combination of those vectors. And we're going to call these such values of phi, if they exist, we're going to call rank 2 attractor varieties. So now back up at 4. So we saw the Bayes conjectures, and we saw the zeta function, and we saw that a zeta function can factors, and it can be written as a product of polynomials R of degrees given by the Betti numbers, and something that perhaps, well, it was said, something one can show, and Dwork showed, was that each R, in fact, is a determinant of the inverse Frobenius map acting in this way, acting on the cohomology in this way. And indeed, it was by showing this that Dwork showed that the zeta function factored in the way it does, where the degree of R is the degree of RK in this factorization is the K Betti number. For a one parameter threefold, it's a fact that it's a fact based on the definition of a Calabi-Yau manifold that there are no one forms and there are no five forms. And I'm talking, of course, in 3 dimensions. So there are no one forms and no five forms. So R1 here and R5 are trivial, they're just one, so they go out. And the numerator is just R3, and from now on I drop R3, I drop the 3. So the denominator, at least in simple cases, the denominator is very simple. It's just generalization of what is the case for elliptic curves. You just get the factors 1 minus t, 1 minus pt, 1 minus p squared t, 1 minus p cubed t. All the interest is in this factor in the numerator, which generically is a quartic polynomial t, again, as we saw before. But now something interesting happens. So suppose we have a rank 2 attractor. That means that there's a lattice, that omega, that the H30 plus H03 is a lattice plane, and the orthogonal plane, you have a symplectic inner product, so there's an orthogonal plane. The orthogonal plane is also going to be a lattice plane. So the lattice breaks up over the integers into a product of 2 lattices, which means that you can take the third cohomology and factor it into 2 2x2 blocks over the integers. And so this R, which was the determinant of a 4x4 matrix, and therefore gave us a quartic, actually becomes a product of two-dimensional determinants. And so the quartic factors in this way. Okay, it factors into 2 quadrics. So this is very special, right? It won't generally be the case that you can always factor a quartic into a product of 2 quadrics, but you can't do that over the integers. So what's special is that at an attractor point, the quartic will factor over the integers as indicated. And this is, so you calculate these, so you make lots of tables like this. And so, for example, this is a pretty value, and p equals 19 is both a random prime, but it's also as big as will fit on a page. So do this, and this manifold can be, you have various, if p is 19, then phi can be 0, 1 up to 18. Certain values correspond to singular values. So the singularities, as Senya, I think, mentioned, this is for the Houlic-Verrall manifold. So the singularities are at 0, 1, 1/9, 1/25, like that, and infinity. And where the manifold is singular, you notice that the degree 4 polynomial drops in degree to degree 3, and the degree 3 factors into a quadratic times a linear space. It happens at every singular value. But somehow I've lost my shading. Oh. So in converting this to a PDF, we lost the shading. So you'll have to help me. But it factors into 2 quadrics in a couple of cases. So look at entry 4 and entry 5. So the quartic factors into 2 quadrics for phi is 4 and 5, and make a note that 4 and 5 is important, and also make a note that 4 and 5 are actually the same. Okay, which was a bit of a surprise. 4 and 5 are actually the same, and it factors again into 2 quadrics where phi is 8, so add that to the list, and it factors again into 2 quadrics for 11 and 9 and 11. 9, yeah. 9 is true and 11 is true. Okay, so you've made a list of those values. Okay, 4, 5, 8, 9, and 11. Okay, so now, okay, here's the strategy. We want to find, what we want to do is find an example of a rank 2 attractor point. And we're going to do it by using this arithmetic method. We want to compute the zeta function for many values of phi and many values of p. And then we look for persistent factorizations. So what's a persistent factorization? We suppose that there's some polynomial g of phi with rational, so integer coefficients, such that the roots of g explain the factorizations. Okay, so it's independent of any particular prime. This is supposed to happen. So the roots of g, if it exists, explain the factorizations for all primes. Okay, and this is the data. So the top graph is the Hewlett-Ferrell manifold, and it's considered for the first 1,000 primes, actually from 7 to the 1,000th prime. Okay, the 1,000th prime is 3583, I think. Okay, and P is 19 is in here, and we saw there were 5 factorizations of the right type. Okay, so there's P is 19, and these the others. And the first thing that struck you, what brought the Hewlett-Ferrell manifold to our attention, okay, was that this graph is exceptional. This diagram is exceptional. This is the same diagram for the quintic. Okay, it looks completely different. Right? It factors, so these count the number of factorizations into 2 quadrics. It looks completely different. There are many fewer factorizations. This seems to be the general case. The graph the diagram looks like this. Also, there's a clue in here, which is, notice that for the quintic, for most primes, there are no factorizations. Whereas for the Hewlett-Ferrell manifold, there's a factorization for every prime. At least one. So this leads you to suspect we're looking for a polynomial whose roots explain these factorizations. Okay, so your first guess is there's a linear polynomial, because a linear polynomial has a root for every prime. Okay. And if you think about it, it's not too difficult. There's some tricks based on the Chinese remainder theorem, and you find that you expect a factor that if 7, 5 plus 1 is 0, then you get a factorization for every prime, except 7. So you expect a certain number of bad primes, but apart from 7, there's a factorization for every prime. And that was easy. I mean, you can imagine doing the search. It wouldn't take you very long to find the value of phi if you look with your search with your computer. But that one was easy. Slightly harder is this one, that once you've got one factorization, you take out all those points and you look at the diagram again, and you see that there's still a lot of factorizations. So having been successful with the linear equation, you then say, well, perhaps there's a quadratic equation, but finding that's harder. So that's a problem you give to the graduate student. And then Mohammed went away over the weekend and he came back on Monday with this equation: 5 squared minus 66, 5 plus 1 is 0. And when that has a root, then the polynomial factors. And the roots then are 5 plus minus 33 plus or minus 8 root 17. Okay, so now a bit of arithmetic. So that's the subject of this talk, right? Arithmetic. So we'll do some. Yeah.
We're missing 8, right?
I'm missing
8.
4, 5. Yeah, thank you. Thank you. There's an 8 here. Okay. Okay, so okay. Think about P is 19. That's the example we looked at. If P is 19, 7 times 8 is 56, which is 3 times 19, 57 minus 1. So in fact, this is minus 1, mod 19. So in fact, minus the 7th is 8 mod 19. Yeah. You look as if I'm trying to sell you a rusty car. No? No. Okay, let's go on. Right, I mean, we're looking for a root of the equation 7, 5 plus 1 is 0. And what we're saying is that if phi is 8, then 7 times 8 plus 1 is 56 plus 1, which is 57, which is 0 mod 19. Yeah, so this is true. And 8 should have been in this list. We did say 8 is in that list. And then if P is 19, then notice that 17 is 6 squared, because 17 is 36 minus 19. So it's 6 squared mod 19. So 5 plus or minus is 33 minus plus minus 8 times 6, 48, and 33 is 14 mod 19, and 48 is 33 is 14 mod 19. And 38, yes, 2 19s is 38, and 48 is 10 mod 19, so you get either 24, which is 5 mod 19, or you get 4 mod 19. Okay, and 4 and 5 are in the list, and 4 and 5 are the same. And 4 and 5 are the same because they're roots of 5 squared minus 60. They're the roots of the same equation. Okay. Okay, now the pretty thing is it's not just true for P is 19, it's true for all primes, right? And this one is true whenever 17 is a square, mod P. So we recover in this way rational numbers, right? Well, we go rational numbers, or at least when phi is minus a 7th, we recover a rational number. And when phi squared, we recover an algebraic number, which is the root of this quadratic equation.
Okay. Comment on 9 and 11?
No, 9 and 11 are random. And I mean, there are, we don't suppose that this explains all factorizations. The reasoning goes one way. Okay. If phi is minus a seventh, it always factorizes. If phi satisfies the quadratic equation, it always factorizes. We don't suppose that every factorization is one of those cases. Okay, and we said that there was a diagram like this, which doesn't usually happen. But once we have these rules, once we say phi is minus a seventh, I think this is the diagram for phi is minus a seventh, then you can draw this flow diagram and it actually works, right? The flows, you start somewhere and the lines flow into the attractor point. So the axis is here, it's on the axis, this is minus a seventh, this is 0, these are the singular values, this must be a ninth, this is 1 over 25, this is phi, I'm not sure, this is 1, right, this is 1, and the other point's wrong off the diagram. Okay. But there's more. There's more information in the tables than the existence and location of the attractor points. So if we say we look at phi is minus a seventh, then you find that it breaks up into two quadrics, but it gives us two coefficients, alpha p and beta p. Okay. And it is the case, you look these up in the LMFDB, the database of modular forms, and you find that there are two modular forms, one of weight 2, one of weight 4, for the group gamma 0 of 14, such that F2 is the sum of alpha n q to the n, F4 is sum of beta n q to the n, and when n is p, when n is any prime, then the alpha p down here is the same as the alpha p up there, and the beta p down here is the same as the beta p up there. So you have something that if you're a mathematician, you say, of course, right, it fits in with the Serre conjecture and other things. You know that when you have a motive of length 2, then it leads you to modular forms. But if you're a physicist, this has sprung at you out of the vacuum, right? Why, you had a black hole, why is there a group gamma 0, 14 involved? Why are there modular forms for that group involved? Okay, and I should say there's a similar story for the quadratic, the other quadratic equation, phi plus and minus. There's also a story about there, the group is gamma 1 of 34, and there's a similar story about modular forms. So associated with the modular forms are L functions. So you take these modular forms, F2 and F4. From these, you can form an L function by taking these Mellin transforms. Q is e to the 2 pi I tau, so e to the minus 2 pi y. Okay. And then another thing that happens is that the periods of omega are given by simple rational values. So we evaluate the periods at phi equals minus 7. And the values of the periods are given by simple rational multiples of L41 and L42, critical values of the L function. So, okay, there's a natural basis of periods. The Xenia gave you these pi's. If you divide by pi, by appropriate powers of the number pi, and take the real part, then you get these objects psi, j, and phi. And when phi is minus the seventh, we have psi 0 is 7 L4. There's a transcendence degree with these things. The L4 of 2 has degree 2, so you want to divide by pi squared. Psi j also has, you want to divide by pi to the j. But if you write it that way, then there's a coefficient here, 7. Psi 1 of pi is 5 halves L4 over pi. L4 1 of pi, and then psi 2 is minus 7 thirds, L4 2 of pi squared, and psi 3 is this, 11 halves here. Okay, so you get these relations, which of course normally you would never have, right? You solve a linear, the period satisfied a degree 4 ordinary differential equation. You take a degree 4 ordinary differential equation and you look at the solutions and you evaluate them with phi is minus the 7th, you will never find a rational relation. You will not, in general, find a rational relation between periods. And here we have 2 rational relations, and that's because it's an attractor point of degree 2. How am I doing for time? Not
10 minutes.
Oh, okay. I may finish on time.
Okay, so 15. 15.
15. I may finish on time. This will be a very special occasion. Okay. Okay. So there are these relations. If you divide out by the required values of pi, you get this and this, the two linear relations on the periods. And yeah,
One thing. So you say that this happened, then the attractors are defined over Q, right? This is what these slides mean.
the attractors are defined. Yes. So well, phi is minus the 7.
So this is like with the small conjecture when you have, because they have this conjecture of when an attractor could be defined over Q. So this is
phi is defined over Q.
Okay.
The other one is defined over Q root 17.
I see.
Yeah. So you've got this, and you might say, do you have a proof? Someone asked me if I have a proof.
What?
Do I have a proof? Ask me if I have a proof.
Do you have a?
Yeah. Do I have a proof? No. Okay. But we calculate everything to 1,000 decimal places, and it's true. Okay. Okay. And the other thing, so here is really sort of the high point, that you can go back and you can look, there were certain charges, right? There were P's and Q's. And given phi is minus the 7th, you can tell what the P's and Q's are. So you get a PQ vector here, and there's something I've hidden. There are really 2 models here. Kappa can be 1 or kappa can be 2. I won't go into that. Kappa, there are 2 ways of constructing models here. One has kappa as 1, one has kappa as 2. But you get a family of possible charge vectors by taking the linear span of these two vectors. And there's a number that occurs, we call it V star. It's 7L4 of 2 over pi L4 of 1. So these were the L values that occurred on the previous slide. And if you work out, you can now work out everything, including the area of the horizon. And the area of the horizon is very much a physicist's number, right? No one's going to argue with that, I don't think. And the beautiful fact is that here you've got this number, which is in the province of physics. And there's some interesting facts about this. There's an overall coefficient, which we don't understand, but we notice that it involves 14, which is also occurs in the conductor here. And then you get a 2-parameter family depending on integers k and l, and it involves this v star here, k squared v star, and then this squared, and it involves one of the v stars. So these number theoretic numbers for which there's no physics explanation yet occur in the formula for the area. Right, and this is interesting, right? The area, the entropy of the black hole is a quarter of the area. So this area basically tells you the number of ways you can make the black hole from simpler constituents, whatever they are. Right? And it involves L functions, which, of course, famously also involve counting problems. So hopefully there's something here to unravel about what exactly is being counted. Then I could write down similar expressions for the other attractor point involving the quadratic equation. Here there will be that would involve gamma 1 of 34. You get 34 here, and again there's a slightly different definition of V star. Right, I think I've got it. Okay, for the other attractor point, there's also, it breaks up, and there are also two modular forms, this time for gamma 1 of 34. This is the LNFDB classification of those forms. And there's, if anything, a neater formula. And you write down this V star, lambda 4. Lambda is the real part of L4. Lambda 4 is the real part of L4. So you write something down involving the real parts of the L functions. There's a coefficient that looks strange, but in fact, if you look at the norm of 9 minus root 17 over 2, it's 64, which is 8 squared. And so if you replace this by 8 times a unit, you see that this coefficient is 34, which was the conductor, times a unit. And the area, again, the 34 appears here for reasons we don't understand. But then you get this very nice form, k squared over v star plus x squared v star for the area. So these are our favorite formulae. Nice. Okay, and then we get to say something about Chebyshov, okay, which is, have we finished? Right? We found a linear equation which explained the factorization, some of the factorizations. We found a quadratic equation which explains some of the factorizations. And then you could ask, are there more? Right? Is there a cubic equation that explains more factorization? And it's here that we bring in Chebyshov, and there's a corollary to Chebyshev's theorem that says that over Fp, an irreducible polynomial f with integer coefficients has on average over P 1 root. Okay, so for a linear equation, it's easy. For a linear equation, you have a root for every P, so you have 1 root. And for a quadratic equation, you have 2 roots half the time and 0 roots the other half of the time, apart from a finite number of cases. So that's true for linear and quadratic equations. And then for the rest, you have to actually quote Chebyshev's theorem and a corollary to it. Okay, but it's true for all degrees. So if g of phi has, so here's our putative polynomial whose roots explain the attractor points, degree to attractor points. So if that has k irreducible factors, g has on average k roots. Okay, and we already know that this g has 2 factors. We know that 7 phi plus 1 is a factor. And we know that phi squared minus 66 phi plus 1 is a factor. So this has 2 irreducible factors, and it might have more. Okay. But you have a computer, you have Mathematica, you can draw graphs. Okay, this is the number of factorizations. So we have a diagram at the beginning with lots and lots of factorizations. We divide the plot into bins of 150 primes, and we compute the number of factorizations. And you see that it drops. This is for the first 1,000 primes. You see it drops down, and at first we calculated only to 500 primes, and we were here, and it wasn't clear whether this was 2 or 3. Okay, but then you carry on calculating, and of course there's no theorem that it doesn't go up, but it looks compelling that this is converging to 2. And if it converges to 2, then there are no errors. Then there are no more roots of this. Then it converges to 2, and 2 is what we've got. So just to show, this is for the quintic on the same scale. So the scale was, oh no, it's not on the same scale. This is just 0 to 1. So this is very much smaller than the other one. The other one went up to about 5, I think, on the vertical axis. And this is just goes up to 1, and this is 0.5. It starts at 0.5, and it looks, there's a compelling case that's converging to 0. So if you want to find rank 2 attractor points for the quintic, then unless you're a super optimist, you shouldn't look, because unless you're a super optimist, then there aren't any. Yeah. Okay, so thank you.
Let's leave it for the talk. So questions or comments?
I have a question. So I'm not a physicist, right? But when you initially had your, that the black hole is an actual sphere, that graph that you showed with the attractor points, like physically, that whole like light quanta getting closer to the black hole, is the graph that you showed the ellipse moving, or the like just showing the energy going into the black hole?
The point is that gravity bends light. I mean, or if you like, light drops. And so you emit a sphere of light. If you're a long way from the black hole, that's a sphere centered on the point of emission. If you're nearer to the black hole, then that sphere is shifted towards the black hole. Right? And it gets to a stage where it's shifted so much that the surface of that sphere contains the point of emission on the surface.
So the graph that you showed, those attractor points, or that flow, is the movement of that sphere?
No, conceptually it's a different thing. You're asking, can you find such a solution in supergravity, the generalization of gravity associated with superstrings? And the answer is most of the time not. So the properties of the black hole are determined by its charges, if it's supersymmetric black hole. For most charges, there's no solution. If there is a solution, then the charges have very special properties. And those are what will be explored.
No, other questions? Comments? Okay.
Gracias, Felixenia, por estas charlas tan lindas. Maybe I'll ask in English. If somebody is a number theorist, or somebody knows how to count points on varieties but knows nothing about the physics, what is how can they be useful to this program? What are some kind of entry points?
I think this touches on lots of problems to do with modularity. And I mean, formulating some of those problems would be very interesting. But I don't, I mean, if you're saying, how can I help? I'm not entirely sure, but there, I'm sure you can, but I don't have a problem ready to give you.
You can create tables and tables and tables of the numbers. And as Philip says, there is a modularity conjecture to character. It's a conjecture, and it's not clear what how to construct. It's a sequel.
Oh,
yeah.
So there's a lot we don't know about Siegel multiple forms. So and a lot in the tables. So even how to construct the Siegel modular forms. I mean, everyone assumes they exist, but there are very few that you can write down. And something I didn't say, but part of the progress in this has been technical progress with fast computation of Z functions. So I showed you a graph here. You know, it was actually it was actually considerable progress that took many years, actually, to write codes that would calculate for many primes. But there was a time when you could only do this